continuing in section 10.1, addressing amplifier basics, and the first thing we're going to look at here is phase relationships. Signals may or may not be phase shifted as a result of amplifier operations. Amplifiers may be classed as, there will be the inverting and the non-inverting. And inverting would mean that here we had an input and we would see that our output is out of phase with the input, and then with the non-inverting we would have an input and the output would be in the same phase relationship. Input-output phase relationships may be used to characterize amplifier behavior. And this is the amplifier that we had looked at in a couple lessons back. Note here, the red line is here on the input, going over here to the O-scope, and then the blue lead from the O-scope is going down here to the output, and this is the O-scope representation of those two positions on the schematic, and you'll notice that they are 180 degrees out of phase. The red sine wave here is the input. Now, note on your screen here in the O-scope capture, it looks like the output is larger than the input, but actually the output is 147 times larger than the input. But again, the important thing that I'm getting at is that they are out of phase with each other. Now, there is another type of amplifier configuration called a differential amplifier. We may look at that when we discuss differential amps later. They will utilize two transistors. They usually utilize both a negative and a positive voltage, and the first transistor in that configuration would be the inverting, but the other transistor would represent the non-inverting output. So you could tap the inverting or the non-inverting if it's in a differential configuration. Okay, input and output resistance. This is often referred to as input and output impedance. Practical amplifiers have input and output resistances that must be considered. For minimal loading effect, we want a source to have a low output resistance and the amplifier to have a high input resistance. So this is usually when we evaluate this, we're looking at voltage. And so here we have a signal source, and the RO here is indicating the internal impedance of our signal source. So when we say RO, we're talking about the output resistance or impedance. And so whether you realize this or not, all signal sources will have some type of internal impedance, and when they amplify a signal, part of that signal will actually be dropped across the internal resistance of the signal source. Now, likewise, here we have an amplifier, and this is indicating an operational amplifier. And amplifiers have an input impedance, and so here we have Ri, and the I here is for input, and the R is for resistance or impedance. Now, as a rule, you want the impedance to be very large. So you want output impedance to be very small, input impedance to be very large. And here's the reason why. Let's just throw in a couple of values here of resistances, and I'll make them simple so that we can quickly do an evaluation here. We'll say that the output impedance here is 10 ohms, and that the input impedance is 90 ohms. And here we have a voltage, and we're sending in to this amplifier. And if we did a voltage divider here, we could quickly see, let's see if we did 10 over 10 plus 90, and we would find that that is 1/10 or 10%. So in this particular scenario, 10% of the signal from our signal source would be dropped across the internal impedance of the signal source, and that would leave 90% that would actually get over here to our amplifier and get amplified. And so that would be desirable, that most of our signal is in fact getting to the amplifier to be amplified. Now, if we reverse this scenario and this was 10 and now this was 90, this would not be desirable because now only 10% of our desired signal is ever getting to the amplifier to be amplified. So this would not be good. So you want to have a low output impedance and a high input impedance. With these operational amplifiers, a common input impedance is in the vicinity of 2 megohms, and they're optimized purposely to make a huge input impedance so that when you send a signal to them, they capture nearly all of the signal that is sent to them from the signal source. Okay, input and output resistance. Now, for maximum transfer of power, now notice that we're not talking about voltage now, we're talking about transfer of power. The output resistance of the driving circuit should be equal to the input resistance of the driven circuit. And so here we have a speaker, common speaker impedances are 8 ohms, and so let's put in a ground here and then we'll send a volt or a connection to our speaker. And so for maximum transfer of power, it would be desirable that this have an output impedance of 8 ohms. And that can be mathematically proven. We're not going to go there, but just as a quick analysis, if we considered that this was down at say 1 ohm, then we would see that most of the signal would be dropped across the amp. If we increase this to infinity, then we would get all of the voltage, but the current would be negligible, and so we would have, again, our power transfer would be very small. And so, as I said, it can be proven mathematically that for transfer of power, these should be matched, so that half of the power is dropped here, and half of the power actually is dropped across the speaker, or the load. Okay, classes of amplifiers. Amplifiers may be classed in different categories based upon their application or operation. And there's wide use of amplifiers. There are voltage amplifiers, current amplifiers, power, impedance matching, and then there are several classes, AB, C, D amplifiers. There are logarithmic amplifiers. I have a note here. Please see the discussion in your text addressing characteristics and typical applications. And there are a number of other amplifiers addressed there, and so don't memorize them, but do look at the different characteristics and different applications for amplifiers.